Hope you are very clear with the Coriolis component of acceleration, which was explained in the previous video. Now we can move into an example. So here you can see the question. I will read out the question. A mechanism of crank and slotted lever quick return motion is shown in the figure. So you can see the figure here. So hope you are clear that this Coriolis component is applicable only for crank and slotted lever or any other quick return motion mechanisms. So whenever you see a question like this where you have the crank and slotted lever quick return motion mechanism, you have to think that here you have to consider the next component, that is Coriolis component of acceleration. So we'll continue. If crank rotates counterclockwise, you can see the direction in which the crank is rotating. It is rotating counterclockwise at 120 rpm. So rpm means it is nothing but n value. N is equal to 120 rpm. Determine for the configuration shown. First one is velocity, you have to find out, and acceleration of ram d. So you can see the ram d here where the slider is fixed, which can reciprocate or move in a linear direction. So you have to find out the velocity of it as well as the acceleration for it. And also you have to find out the angular acceleration of the slotted lever. You can see the slotted lever OC. So for this you have to find out the angular acceleration. So angular acceleration means you have to think that you have to find out the tangential component of acceleration for the link OC. Then only you can get the angular acceleration alpha for that OC. So that is what we have to find out. And also the lengths are given. Crank length AB is equal to 150 mm, slotted arm OC equal to 700 mm, and link length of CD is also given, that is 200 mm. So the given data, you can see n value is given. N of AB or BA is 120 rpm. So you can find the angular velocity omega BA 2 pi n by 60. Value is 12.57 radian per second. So and other values are also given in the question for link length. So from this value of angular velocity you can find out the linear velocity of the link AB. So that is VBA, B with respect to A, or B given A, anything you can write, is equal to angular velocity into its link length. Angular velocity we have already found out, that is 12.57 into 0.15, that is 1.9 meter per second. So this is the initial calculation what you have to do from the given data. Now we have to move on into drawing the space. See how we can draw the space diagram. So before drawing the space diagram, so you should see the values. You can see the length OA, it is 400 mm, and A to D is 300 mm. The link lengths are 150 mm, 700 mm, 200 mm, etc. So values, if you convert into centimeters, it will be some 40 centimeter and 30, 15, 70, 20, like that. So what I will do, I will use a scale 1:10. I am dividing everything with 10. So the values I can get for OA as 4, AD as 3, then crank length will be 1.5, and OC, the slotted lever OC, will be 7, then CD, the short link which connecting the ram, will be 2. So that will be nominal. So you can start drawing in that manner. So we'll do the drawing. So space diagram. So we'll start with point O. From the point O you draw a vertical line of measurement 4 centimeter. Mark the point A there. Then from A you can draw a line, horizontal line. The distance between the horizontal line and the point A should be 3 centimeter. So you can simply draw that 3 centimeter. So simply mark the point 3 centimeter from A and draw the horizontal line. Now from A as center, AB as radius, you can draw an arc on the 45 degree inclination. So you can get the point B dash. So you have to keep in mind here, you have a slider B and you have a point B dash. So that is the coincide point here. Okay, so here when we are finding the Coriolis component, you have to find the Coriolis component of slider acting on the coincide point. That means B acting on B dash. So we'll go in detail when we reach in that position. So you can get the point B over there. So you can just show the slider with any measurement. From there, what you have to do is you can simply join O to B dash, and you can extend along the same length. What is the total length required for OC? The slotted arm is 7. So from O, measure 7 centimeter along the line OB dash and keep on extend to get the point C. So you can get the point C also. Now from the point C, you take the CD length. CD length is 2 centimeter. Draw an arc which is falling on the horizontal line. So there you can mark the point D. So there you can finish the diagram by drawing the slider with a fixture. So like this, we will be drawing the space diagram. So don't forget about mentioning the scale, that is 1:10. So now we can see the space diagram which we have already drawn. So this is a space diagram. So according to space diagram, we will draw the velocity diagram also. So when we draw the velocity diagram, we'll start with any fixed point. So fixed point, we'll mark it as O and A. Since O and A is the fixtures there, so that is a fixed point. From there, we'll start drawing the velocity of the crank AB. So from A, you draw a line which is perpendicular to the link length, that is AB dash in the space diagram. So perpendicular, so draw. So what is the length? Length we have already found out, that is 1.9. So you can directly take that same value 1.9. If you're converting into scale also, it is possible, but don't forget to convert it back when we have to find out the velocity of other link. So here, to remove that confusion, I'm just directly taking 1.9. So I'll draw 1.9 from O in this direction, and we'll get the point B. So we can take that point B there. Now we'll move on to next link. So next link is the link slider. Okay, so slider can only slide in this direction, but where we have to start, you can start from point B, then point B. From B, we'll start drawing the velocity of slider. You can see this is the direction. So this direction you will draw. I don't know where to end. You can keep on extending. Then I will keep it like that. Now we'll go to next link. Next link is OB dash, link, rigid link OB dash. So this is the direction perpendicular to link. Where we have to start? You have to start either from O or you can start from B dash. Since the point B dash is not available initially, so what I will do is from the O, I will start drawing in this direction. So this line and the line which I am extending from B both will meet at one single point, that is the B dash. That is how we are getting the point B dash. So you can mark the point B dash there. Now you have to get the point C. So you have to extend that. So you know how to do it. We have taken the ratios. Similarly here also you have to take the ratios and find out the point C. So what is the ratio will be? What we have to find out? We have to find out B dash C in the velocity diagram. So small B dash C divided by the capital B dash C from the space diagram is equal to O B dash, small O B dash divided by capital O B dash. So this ratio will take, and we'll find out the value of B dash C we require in the velocity diagram. So you can get the point C also. Now after that, we'll go to the next link. Next link is simply CD. So CD, this is the link. So for this link, the direction of velocity will be perpendicular. So perpendicular means so we have to start from either C or D. Since the value of D is not here, the point is not there, you will start from C. This direction you will draw. So we'll extend that. I don't know how much I have to extend. Next, you have to draw for the slider D. Slider D, you have to start from either point D or you have to start from fixture. So point D I don't know, so I'll start from fixture from OA this point, so it can only move in this direction. So you can extend that both that velocity line and the velocity line of CD will meet at one point. The point is D, so that is how you are getting the point D also. So in this way we have completed the velocity diagram of the given mechanism. Now you can see two things. One, in the B dash side, you can see if you want to find out the velocity, direction of velocity, where B dash B is there, it will be upward, and the velocity B dash will be downwards. So that is very important when you have to consider the Coriolis component. Coriolis component of acceleration is based on the velocity. So velocity what we have to take is B dash B, that is B dash. B dash means B slider, B dash is the coincide point. So slider acting on the coincide point. So slider is B, so B will be acting on B dash. So that direction, you can see the downward direction, B velocity of B dash, that direction you have to take when you are considering for the Coriolis component. Now from the velocity diagram we can get the velocities of different links. So first and foremost we can get the velocity of the slider with respect to the coincide point. So that is B with respect to B dash. So you can see this B with respect to B dash, that if you measure I'm getting 1.05 meter per second. Now we can move to the next link, that is DC or CD. Here I am not considering for the crank because crank we already know. So we can go to DC or CD. That velocity is V D given C, that is vector CD 0.45, that is the value you can measure and check. Similarly for the link OB dash. Similarly for this link OB dash is nothing but the vector OB dash, that is 1.55, and velocity of C, the whole link, whole lever arm, that is C with respect to O, we have to measure the whole distance, vector OC, which is equal to 2.15 meter per second. So question, we have to find out the velocity of ram D. So if you want to find the velocity of ram D, you have to measure VD, that is vector OD, so that is 2.15, that is the first part of our answer, and second part of our answer is angular velocity of OC. Angular velocity of OC is velocity by its linear velocity by its link length. Linear velocity we have VCO divided by OC, that is 2.15 divided by the link length 0.7 equal to 3.07 radian per second in anti-clockwise. So that is the direction which we can have. Now we'll move on to the next part, that is to find out the acceleration of ram D. So for finding out the acceleration of ram D, we have to draw the acceleration diagram. So for drawing the acceleration diagram, we require the radial components, or if we have tangential components, that also for all link, then only we can draw the acceleration diagram. So this part you are very familiar because we have done many problems in that. So I'll just run off with the way to draw the acceleration diagram, and we can see it. So first we can see we have different links. The first link is link AB, so we have to find out the radial component of AB. Then we have to consider the slider with the coincide point. So keep your this thing here, that the slider with the coincide point, that means that can slide as well as it can rotate over the lever OC. So they can have only the Coriolis component of acceleration. You don't have any radial component there. You can have only Coriolis component of acceleration. So how to find out this Coriolis component? So that we'll discuss next. So we'll see what are the links remaining. So next is link CD. So we have to find out the radial component of link CD also. Then we have to find the radial component of link OB dash also. And we require for OC dash, but OC dash we can get by extending, by taking the ratios of OB dash. So if you find out OB dash, that is fine. So I'll just write down the value. So first radial component of the first link, that is crank. So AR of B given A, or B respect to A, that is omega square into AB, or V square by link length will give you. So the value is 23.7 meter per second square. Next, Coriolis component. So in order to find the Coriolis component, you can see the given figure. So this is the condition we have to use. So how we are getting this condition is, so we can check this in the velocity diagram. So if you go to velocity diagram, for the velocity of B with B dash, B dash, you can see it is acting downwards, and it is acting downwards, that direction of velocity. And you can see in the space diagram how it is rotating anti-clockwise, or that is counterclockwise. So counterclockwise downwards. So the direction of the Coriolis component will be in this direction. You can see the direction. So it will be opposite to the direction of rotation. So this is the direction you have to take. This is the direction of Coriolis component. Now we'll write down the value, how much it is. That is AC of B given B dash. It is nothing but it is 2 omega into V. So that is 2 into omega. Which omega you have to take? You have to take the omega of OC. Omega of OC, that is what you have to take, because this Coriolis component is happening on the link OC. Don't take for OB, that is we don't have anything like that. So we have to take for OC. That is 2 into 3.07 into that velocity B given B dash. So that velocity we already have, that is 1.05. So if you multiply every value, you're getting 6.45. Now you can go to the radial component of next link, that is AR of T given C. So V square DC by CD, that is 1.01. So that value will get. So radial component of next link, that is B dash given O, or simply B dash O, that is V square B dash O by B dash O, that is equal to 4.62. So these are the radial components with which we have to draw the acceleration diagram. So in order to draw the acceleration diagram, so these values, you can see these values, if you directly take in centimeters, it is not possible, because one value it is 23.7 and 6.45. So if you divide every value with 2, it may be nominal. Yes, it may be nominal. Or if you can divide by 3 also, you will get the value. So appropriate scale you can take, and you can draw the acceleration diagram based on this. So now we can move into the acceleration diagram, how we are drawing the acceleration diagram. So this is the acceleration diagram you can obtain. So for you, I can explain this again, how we are getting this acceleration diagram. So you can see we'll start with a fixture, that is O dash A dash, which is our fixture. So from there, first we'll draw the radial component of the link AB. So link AB will be acting in this direction downwards. So in that direction I am drawing. The length of it is, it's very 23.7 is the radial component length. So that you can convert into proper scale. So that length you have to draw from this O dash A dash in this direction. So we'll get the point B dash. So got the point B dash. Now from there, B dash as center. Now we have to draw the radial component of, or simply you can draw next the Coriolis component of acceleration you can draw. So from B as center, Coriolis component, you can see the direction of Coriolis component is like this. So this direction you have to take parallel to this direction. So the value of Coriolis component is 6.45. So 6.45 converted to appropriate scale you draw there from B dash. So you get the point X. Now the point, from the point X, now we can draw the radial component of it. So the radial component of B dash. So radial component of B dash you can draw. So we have not found out the value of radial component of B dash. That we cannot get it directly. So now what we will do is, from x you can just draw perpendicular, because you know very clearly that this Coriolis component is nothing but the tangential component of a link. So a radial component will be perpendicular to it. So the radial component, if you want to find out the radial component, so from the point x draw a perpendicular, keep on extending. I don't know where to stop, so just keep on extending, leave it like that. Now we can go to the next link. The next link is the link OB. Okay, so link OB dash, sorry. For link OB dash, we have the radial component. So from where you have to start, we have to start from O dash. So from O dash, I will start drawing the radial component in this direction. The direction along the link length, pointing towards the center. So downwards you will draw. So downwards, so the measurement of it is 1.55. So 1.55 will draw downwards. You got the point y. So from y you will draw the tangential component of it. The tangential component, I don't know the value, so I'll simply extend it. So both will meet at one single point. So both means the both tangential component of the link OB dash and the radial component of the slider with coincide point, that is B dash. So both will meet at one single point, that will be B double dash. So B double dash is the required point. So if you want to find out the acceleration of the link OB dash, so what we will do is we can just simply join O dash and B double dash. So this is the acceleration. So if you want to find out the acceleration of the full length of this arm, slotted arm OC, so what we'll do is we can extend that by the appropriate ratio, taking appropriate ratio like we have done in the velocity also. So that same ratio if we take, we can extend that to this value, so that same along the same length. So in that manner we'll get the point C dash. So after getting the C dash, we'll move on to the next link, that is the link CD. So for CD we have the radial component. The radial component value for CD is 0.45. That is very small value, 0.45. So 0.45 you have to draw along this direction, that is along the link length. In that direction you will draw. So the radial component you can mark it as Z. Then from there you have to draw the tangential component. Tangential component will be perpendicular. So perpendicular you keep on extending and finish, keep it like that. Now we'll move on to drawing the acceleration of the slider D. So acceleration slider D will be only along the linear direction. So we have to start from either point D or the fixture. D point is not here. You'll start from fixture O dash A dash. So from there you draw a line, both will meet at one single point, that is a point D dash. So that is how you can complete the diagram, acceleration diagram, and you can join all the points in order to get the real acceleration. So various points. So in this manner we can finish the acceleration diagram. Hope you can easily understand, because we have done a lot of problems based on this acceleration and velocity. So method will be very clear for you. That's why in detail, and I'm not showing the each steps. So I just explained and went through. So this is how we'll finish the diagram for acceleration. Okay, now moving on to the last part of the question, that is we have to find the acceleration of the ram. So acceleration of the ram is nothing but it is the AD. So by measurement from the acceleration diagram we'll get, that is vector O dash D dash. So measure this distance. So that is what I'm getting is 8.4 meter per second square. So we got that. Next part is find out the angular acceleration of the slotted lever. So angular acceleration of the slotted lever means you have to take the tangential component of the slotted lever. Slotted lever tangential component is nothing but it is YB dash. So tangential component of slotted lever, you can take it as AT of B given O, that is nothing but vector YB dash. So this is the length measurement. So that is what I'm getting is 6.4 meter per second square. So angular acceleration alpha O B, or you can take it as B O B dash O, So that is alpha BO is equal to AT, tangential component of P dash O, divided by its link length, that is 6.4 we got, divided by 0.52 link length is equal to 12.3 radian per second square. So that is acting anti-clockwise. So this is the final answer for the problem. So here you can find that, so here the only difference compared to the previous problem is that here we are considering Coriolis component also for a slider which is sliding along a link which can rotate. So that is the only difference here. So in exam, if they are asking any question concerned with quick return motion mechanism, you have to consider along with the same previous steps one more component, that is AC of that B dash O or B dash P or whatever it is, slider with the coincide point. So that value you have to consider. So that will be the only extra part, remaining everything will be similar. So by this we are finishing our concept of velocity and acceleration by graphical